Hi everyone, and welcome to Module 9, Lesson 3. In this lesson, we're going to talk about the thermodynamics portion of this module. So for this, we're going to use the terms thermodynamically favorable or thermodynamically unfavorable. In the videos that I've posted, they have used the old terminology of spontaneous and non-spontaneous, okay? So spontaneous means it's thermodynamically favorable, and that means it will occur without aid. So thermodynamically favorable reactions are reactions that occur without aid. Thermodynamically unfavorable reactions are those that do not occur without aid. So they need some help, so that makes them non-spontaneous. But just know that those terms are interchangeable, but we want to use the terms thermodynamically favorable and unfavorable because someone somewhere decided that these are better terms for us to use. So whatever, we'll just do it. So when we talk about our thermodynamic favorability, we, yes, need to talk about enthalpy, but we also have to look at something called entropy, which is the measurement of disorder or chaos. And again, super important, we have to understand what the signs mean. If delta S is positive, it's becoming more chaotic. If delta S is negative, it's becoming less chaotic or more ordered. For example, cleaning. Cleaning is going to be a decrease in entropy because it's becoming less chaotic, more ordered. Let's see, things that would become more chaotic. I don't know, the way I cook in the kitchen is more chaotic. Because I'm constantly, there's becoming more and more chaos because I can't clean as I go because that would make my life too easy. So entropy, again, the measurement of disorder or chaos. We can solve entropy the same way as we've solved enthalpy, the sum of the S of the products minus the sum of the S of the reactants. So it says a solid to a liquid to a gas, an increase in heat, an increase in the number of particles, an increase in molecular complexity, all increase the chaos. Okay, let's calculate the standard molar enthalpy for nitrogen gas as given the following information. So we have the total here, and we have the equation, and we just need to figure out what is this nitrogen. Okay, that's fine. So I'm just going to use this equation right here. So the total, 605.9 joules per moles times Kelvin is equal to products, the nitrogen, which is X, plus I have 4 of the waters, which is 188.7. Those are all of my products, minus my reactants. I've got N2H4, which is 121.2, plus I have 2 of the hydrogen peroxides, 109.6. Go ahead and do this math. And just like the other one, I want you to stop. I want you to try to get the answer yourself. X will be equal to 191.5 joules per moles times Kelvin. Okay. So make sure you can get that answer. So that's entropy. Now, a reaction will always be thermodynamically favorable if it is exothermic and increasing in chaos. A reaction will always be thermodynamically unfavorable if it's endothermic and decreasing in chaos. While it's not super important that you memorize this piece of information right here, it will help you for some questions where you won't actually have to do a calculation because you know that fact. But if not, you can do the calculation to determine Gibbs free energy, which is delta H, which will help us determine if a reaction is favorable or unfavorable. And that equation is delta G equals delta H minus T delta S. Okay, super important again with our signs. If delta G is positive, it's unfavorable. If delta G is negative, it's favorable. So we want to determine if this reaction will be thermodynamically favorable or unfavorable at 25 degrees Celsius. We're given the equation, we're given a delta H and a delta S. We just need to determine delta G. So if you look at this equation and these units, kilojoules, joules, moles times Kelvin. I'm going to take this 25 degrees Celsius, turn it into Kelvin, 298 Kelvin. It's always super important that we pay attention to our units, okay? And I'm going to turn the delta S into kilojoules. So my delta S will be equal to negative 0.825 kilojoules per moles times Kelvin. And then I can just plug it into my equation. Delta G equals 196 kilojoules per mole minus 298 Kelvin times negative 0.285 kilojoules per moles times Kelvin. When I solve this, my delta G will be positive 280.93 units kilojoules per mole. Typically, when we're doing these problems, the number itself doesn't matter. The only thing I'm looking at really is the sign. The greater it is, the more favorable or unfavorable it will be. That's basically what it is. But delta G is positive, so this reaction will be thermodynamically unfavorable. That's it. So you can see this in many different combinations. I know delta G, I know delta S, determine the delta H. I know delta H, I know delta G, determine the delta S. I know delta G, delta H, and delta S, determine the temperature. So, you know, any kind of algebra problem that you could possibly see. And of course, there are plenty of practice problems with Gibbs Free Energy in the homework packet that you can look at. And again, if you want to go over any more, you have any questions, please just put it in the chat or ask me and I can go over whatever you want at the end of class. Now, these notes are a little bit shorter. We only have one more thing to look at, and that's going to be, I don't even know what number this is, but another way to determine delta H, and that's by looking at bond energy. So we know that bond energy is the energy needed to break the bonds in 1 mole of a gas into their gaseous product. Again, just another way to determine the enthalpy for a reaction. So to determine the delta H for this reaction, when we're looking at bond energies, we can look at the bonds that are broken, the sum of the bonds that are broken minus the sum of the bonds that are formed. Bonds that are broken, this is important, are the reactants, minus the bonds that are formed are the products. So this is different. Everything else we looked at was products minus reactants. In this example, it's reactants minus products. Please don't get it twisted. Keep in mind, it always requires energy to break the bonds, and energy is released when forming bonds. Whether a reaction is endothermic or exothermic just depends on which one is larger. So use the bond energies that are given here to estimate the enthalpy for this reaction. Now, in order to do this properly, we kind of have to draw out the Lewis dot structures, just so we can see what type and how many of each bond we have. So C2H4, plus H2O gives me C2H5OH. So that's what I have. So bonds broken. So we're going to do delta H is equal to the sum of the bonds broken. So I have a C double bond C, which is 602. I have 4 CH bonds, so 4 times 413. That's the first reactant. And then I have 2 OH bonds, which is 463. And those are all of my reactants. Now I'm going to subtract that from my products. I have, what is that? 5 CH bonds. 1, 2, 3, 4. Yeah, so 5 times 413 plus I have a CC single bond, which is 346, plus I have a CO bond, which is 358, and then I have an OH bond, which is 463. When I do that, I'm going to write it over here, my delta H. Again, you should stop, try to get this answer, make sure you're able to put this in your calculator correctly. I don't want you to do all the work correctly and then end up getting the wrong answer because you put it in your calculator wrong. The final answer should be negative 52 kilojoules per mole. So this is an exothermic reaction, and my enthalpy is negative 52 kilojoules per mole. Okay, and that's actually it for these notes. That was our thermodynamics portion with Gibbs Free Energy and Entropy. And a final way to calculate delta H. That's the last way we're going to look at in these notes. So if you have any questions, please make sure you ask them, especially on some of these things. These notes aren't very long, so it's just practicing these equations. So if you have any questions, please put them in the chat or ask them at the end of class, and I will see you later.